Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm comfort or clarity, please subscribe to the channel. Gently tap the like button and leave a comment to let us know you were here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. Now, let's gently explore something many of us have felt, even if we've never named it. There is a moment, quiet, unremarkable, when you press a finger to a small cut and feel the faint sting of something beginning. You don't think much of it. You reach for a bandage, perhaps. You move on with your day, and by the time you remember to check, the wound has already started closing. Silently, without your direction, without your awareness, without your permission. This is where our story begins. Not in the dramatic theater of surgery, not in the crisis of emergency rooms, not in the noise and urgency of medicine at its most visible, but here, in the ordinary, in the paper cut that heals before you remember it was ever there, in the bruise that blooms purple, then fades through yellow and green across the span of a week, the color draining out of it like a slow tide, in the broken bone that, given enough time and stillness, becomes whole again, stronger in some places than it was before. Healing is one of the most constant things happening inside you. Right now, as you rest and breathe and let your mind settle into the quietness of these words, something in your body is being tended to. A microscopic tear in a muscle fiber from yesterday's walk. A cluster of cells in your stomach lining, quietly replacing themselves after the ordinary wear of a meal. A small inflammatory signal being slowly called off as a threat resolves. A neuron somewhere, strengthening a connection that was used today and will be needed tomorrow. You are, at this very moment, being repaired. And most of the time, you will never know it. We tend to think of healing as something that happens after the injury, after the illness, after the pain. We imagine it as a return, a getting back to normal, as though the body has a fixed blueprint somewhere that it consults and then faithfully rebuilds from. But the truth is far more interesting than that. Healing is not a return so much as a continuous process. It is not a destination the body moves toward once. It is something the body does, constantly, in layers, across time, adjusting, signaling, rebuilding, compensating, and sometimes simply adapting to what cannot be fully restored. There is no pause in this process, no rest day, no moment when the body decides it has done enough and sets down its tools. From the first hours of your life to the last, the biology of repair runs quietly in the background, the most faithful background process you will ever have, requiring no login, no instruction, no gratitude. This documentary, this slow, unhurried exploration, is an invitation to look inward, not with the eyes, but with curiosity, to understand, in plain and careful language, what is actually happening beneath the surface of skin when something goes wrong and the body begins its quiet response. To understand healing not as something magical or mysterious, but as something deeply biological, deeply ordered, deeply, almost remarkably intelligent in its coordination. Not because cells think, but because billions of years of evolution have shaped living systems that respond to damage in extraordinarily precise ways. This is, at its heart, a series of simple science explanations for beginners, an accessible window into the biology of repair. You don't need a medical degree to follow this. You don't need any prior knowledge of biology or chemistry or anatomy. What you need is only what you already have, a body of your own, and a quiet willingness to understand it a little better. And perhaps that is the most important place to start. Not with complexity, not with scientific vocabulary, but with the honest acknowledgement that the body you live in is doing something extraordinary every day that most of us have never paused long enough to notice. So let us begin where the body begins. At the surface, at the moment of disruption. Imagine a small cut, perhaps on the pad of your thumb, from a kitchen knife or the edge of a page. You feel the sharp instant of it. You see the red appear, and in that single second, before you've even fully registered the sensation, before the pain signal has fully completed its journey from fingertip to brain, your body has already begun. Blood vessel walls have constricted slightly at the site of the break. Platelets, tiny cell fragments floating in your blood in enormous numbers, have already begun gathering at the wound's edges, responding to chemical signals released from the damaged tissue. A clotting cascade, a series of chemical reactions as elegant and inevitable as any domino sequence, is already underway. This is not slow. This is not considered. This is immediate and automatic. The body does not wait to be asked. And this is one of the things that makes healing so quietly extraordinary. It requires nothing from your conscious mind. It asks nothing of your decisions. It proceeds entirely on its own terms, governed by molecular signals and cellular memory that evolved long before human consciousness had words for any of it. Before we had language, before we had culture, before we had the concept of medicine at all. The repair systems of the human body are far older than any of that. Over the course of this journey, we will trace that process from its beginning to its end, and beyond, because healing rarely has a clean ending. We will follow a wound from the first seconds of injury all the way through to the laying down of scar tissue, or the slow remodeling of bone, or the gradual rewiring of neural pathways after brain injury. We will visit the immune system in its role as both defender and cleanup crew, not as an army, but as something quieter and more careful than that metaphor allows. We will descend into the science of sleep and discover what happens to the body's repair work in those hours when consciousness steps aside. We will consider stress and emotion and what biology actually says, carefully, honestly, about the relationship between the mind and the healing process. We will also acknowledge limits, because healing, as extraordinary as it is not infinite. Some tissues regenerate fully, some do not. Some injuries resolve completely, some leave a mark. And science, at its most honest, is a discipline that holds those facts together: wonder and limitation, capability and constraint, without flinching from either. Throughout all of it, the tone will remain what it is right now: calm, slow, precise, grounded in what is known, careful about what is uncertain, and always respectful of the complexity of what it means to be a living thing trying to remain alive. Let's move inward, gently, as the body itself moves when it heals, quietly, without fanfare, before we can follow the body's repair process through any of its chapters, through skin, or bone, or brain, or emotion. We need to understand what healing actually is, not in the way we feel it, not in the way we speak of it in daily life, but in the way biology defines it. In the broadest sense, healing is the process by which a living organism responds to disruption and attempts to restore functional integrity. Notice that word, functional, not perfect, not identical to what came before. Functional, capable of doing what it needs to do. This distinction matters enormously, and we will return to it often throughout this exploration, because it shapes everything that follows. But to understand healing, we first need to understand the state that the body is constantly trying to maintain, and that state is called homeostasis. Homeostasis is one of the most fundamental concepts in all of biology. It refers to the body's tendency to maintain a stable internal environment despite constant external changes. Your body temperature hovers near 37 degrees Celsius, not because the environment around you is that temperature, but because your biology works constantly to keep it there, generating heat when it is too cold, dispersing heat when it is too warm. Your blood pH stays within a narrow range, because enzymes and cellular processes depend on that range to function correctly. Your blood glucose levels are monitored and adjusted by hormones moment to moment, rising and falling in response to food and activity and stress. The concentration of oxygen in your tissues is regulated with extraordinary precision, because even small deviations can impair cellular function. Every one of these parameters is a moving target being continuously hit by the biology of your body, not because any single cell or organ is in charge of all of it, but because the entire system is designed around the principle of feedback and adjustment. Sensors detect deviation. Signals are sent. Effectors respond. The deviation is corrected, and then the correction itself is sensed, and the correction to the correction is made. Homeostasis is not a fixed point. It is a dynamic balance, a continuous series of adjustments, corrections, compensations, and responses, like a tightrope walker who is never perfectly still, but is always, actively, balancing. When something disrupts this balance, whether it's a wound, an infection, a toxin, a broken bone, a period of extreme heat, or prolonged psychological stress, the body's first priority is to respond, to contain the disruption, to prevent it from cascading into a larger failure, to reestablish, as quickly and as thoroughly as possible, the conditions under which the body can continue to function. This response is what we call healing, but healing encompasses several different biological processes, and it's worth taking time to distinguish them carefully. The first is repair. Repair is the most common form of healing. It is what happens when damaged tissue is replaced, not necessarily with identical tissue, but with tissue that fills the gap and restores structural continuity. A skin wound that heals with a scar has undergone repair. The scar is not identical to the original skin. It lacks hair follicles. It lacks sweat glands. It lacks some of the elastic properties of undamaged dermis. Its collagen fibers are arranged differently, but it is structurally sound. It closes the wound. It restores the barrier. The body has done what it needed to do. That is repair. Repair is pragmatic. It is the biological equivalent of patching something that needs to hold rather than rebuilding it from scratch. And in most circumstances, given the urgency of closing a wound against infection, given the energy cost of tissue reconstruction, pragmatic repair is exactly the right response. The second process is regeneration. Regeneration is rarer in adult humans, but not absent. It refers to the replacement of damaged tissue with tissue that is, in most important respects, identical to what was there before. The lining of your small intestine regenerates almost completely every few days. A remarkable turnover rate driven by the constant mechanical and chemical demands placed on that tissue. The liver has a well-documented capacity to regenerate substantially after certain kinds of damage. The outer layers of skin regenerate continuously, shedding dead cells from the surface while the deeper layers produce replacements. But many tissues in the adult human body, including heart muscle and most neurons in the central nervous system, have very limited regenerative capacity. When they are damaged, repair replaces regeneration. What results is often functionally adequate, but structurally different from the original. Scar tissue where there was once specialized muscle, reorganized neural circuits where there were once specific pathways. The third process is adaptation. Sometimes the body cannot fully repair or regenerate the damaged tissue, and instead, it reroutes. A neighboring brain region may gradually take over some functions from a damaged one. Muscles around an injured joint may strengthen to compensate for reduced ligament stability. The remaining kidney, after one is removed, will enlarge and increase its filtration capacity to compensate for the loss of its partner. The body is, in this sense, astonishingly flexible, not in any conscious way, but in the evolutionary sense. Biology has built-in redundancy, compensatory pathways, and adaptive mechanisms at every level, from the molecular to the systemic. Adaptation is perhaps the most philosophically interesting of the three processes, because it moves furthest from the idea of healing as restoration. Adaptation is healing as transformation. the body becoming something slightly different from what it was, not by accident, but as the most functional response available to it. Now, one more important distinction: the difference between healing and curing. These words are often used interchangeably, but biologically they are different. Curing implies the complete elimination of a disease or condition, a full return to the exact state before illness. Healing is broader. Healing can include curing, but it also includes recovery that leaves some residual change, adaptation that compensates for permanent loss, and the restoration of well-being in the presence of an ongoing condition. A person who loses a limb and learns to move fluidly with a prosthesis has not been cured of their injury, but they may, in many profound biological and psychological senses, have healed. Their nervous system has adapted to new sensory and motor patterns. Their remaining musculature has compensated. Their brain has reorganized its body map. Their gait, different from before, but functional, reflects the biological work of adaptation expressed across months and years of living. A person managing a chronic condition that cannot be eliminated may still, with time and appropriate support, experience meaningful healing, a restoration of functional well-being, an adaptation of biology and behavior and psychology to the new parameters of their health. Biology does not always achieve perfection. It does not always restore what was lost, but it consistently, persistently, moves toward function. And that, perhaps, is the most important thing to carry with us through the rest of this exploration. Healing is not the pursuit of perfection. It is the pursuit of function, of balance, of continued life. And the body, in its quiet and tireless way, pursues it constantly. We need to spend a long time here, because inflammation is, perhaps, the most misunderstood word in popular health conversation today. It is blamed for almost every chronic condition. It is the target of countless dietary interventions and wellness products and lifestyle modifications. It is described routinely as something to avoid, to suppress, to reduce, to eliminate from one's biology as thoroughly as possible. And yet, without it, you would not survive a paper cut. Without it, the first scratch of bacteria entering a wound would spread unchecked. Without it, the body's repair machinery would never receive the signal to mobilize. Let us follow what actually happens in the first moments after an injury. Let us trace it carefully, beginning at the very instant of disruption. Because the speed and precision of what unfolds there is one of the most remarkable things in all of human biology. You cut your skin, the blade, or the corner of paper, or the sharp edge of something ordinary, breaks through the epidermis, the outermost layer of skin, and reaches into the dermis beneath. In doing so, it severs tiny blood vessels called capillaries. Cells are torn, their internal contents, molecules and organelles and proteins that belong inside cells, spill into the surrounding tissue, and immediately, within seconds, a cascade of events begins that will unfold over hours, days, and weeks. The first response is vascular. The blood vessels in the immediate area undergo a brief constriction, a narrowing that lasts only a moment, perhaps a few seconds to a minute. This is reflexive, an automatic response from the smooth muscle wrapped around the vessel walls. It reduces blood flow momentarily, helping to limit the amount of blood lost in those first instants. It is the body's equivalent of pressing a thumb against a leak in a hose. Then the opposite happens. The vessels dilate, they widen, and simultaneously become more permeable, meaning their walls become slightly leaky. Fluid and proteins that normally stay contained within the bloodstream begin to seep out through the loosened vessel walls into the surrounding tissue. This is what causes swelling, that puffiness around an injury, the way a sprained ankle balloons, or a bumped forehead rises into a goose egg, is not random, and not merely unfortunate. It is deliberate. It is the body flooding the damage zone with resources, and those resources matter enormously. Among the things that seep from the dilated vessels are proteins called clotting factors. These, combined with the tiny cell fragments called platelets that have already begun aggregating at the wound site, initiate a process called the coagulation cascade, one of the most precisely regulated biochemical sequences in the entire human body. Each clotting factor activates the next in the chain, like a long sequence of chemical introductions, each one triggering the one after it. At the end of this cascade, a protein called fibrinogen is converted into fibrin. Fibrin forms long, sticky strands that weave together into a mesh, an intricate biological net that traps platelets and red blood cells and forms what we recognize as a clot. The clot serves two purposes. It slows and stops bleeding, which is the obvious one, the purpose we think of immediately, but it also forms a temporary scaffold, a kind of biological framework, over which the more sustained and sophisticated work of repair will eventually begin. That clot is not the endpoint, it is the foundation. All of this, the vasoconstriction, the dilation, the increased permeability, the platelet aggregation, the coagulation cascade, happens within minutes of the injury, and it is driven not by any single cell or organ making a decision, but by a symphony of chemical signals released from the damaged cells themselves. Damaged cells release molecules called damage-associated molecular patterns. Scientists sometimes abbreviate these as DAMPs, which act as alarm signals, molecular distress flares that diffuse outward from the site of injury into the surrounding tissue and into the local circulation. Nearby cells and circulating proteins respond to these signals. The inflammation begins. Inflammation is, in biological terms, a coordinated set of vascular and cellular responses to injury or infection, whose fundamental purpose is protective. It is not a disease. It is not a malfunction of the body. It is a feature, not a bug, one of the most essential features in all of biology. The word itself comes from the Latin inflammare, to set on fire, which speaks to the four classical signs that ancient physicians first described thousands of years ago: redness, heat, swelling, and pain. To these, a fifth is sometimes added: loss of function, the temporary inability to use the injured area normally. All five of these signs have biological purposes, and understanding them changes how the inflammation feels. If not physically, then at least intellectually. Redness occurs because blood flow to the area has increased substantially. The dilated vessels carry more oxygenated blood to the site, giving the tissue a flushed, warm appearance. That redness is a visible sign of the body routing resources toward the problem. Heat is a consequence of both the increased blood flow and the intensified metabolic activity of immune cells that have begun arriving at the scene. Some of the chemical signals released during inflammation also raise the local temperature slightly. An elevated temperature can inhibit the growth of certain pathogens, a detail that suggests, intriguingly, that heat at an injury site is not merely a side effect of cellular activity, but partly a deliberate antimicrobial strategy. Swelling, we've already touched on this, is the accumulation of fluid that has leaked from the permeable vessels into the interstitial space. This fluid carries proteins, immune cells, and signaling molecules. It also physically dilutes any toxins present at the injury site, reducing their local concentration. Pain is mediated by the action of inflammatory chemicals on specialized pain-sensing nerve endings called nociceptors. Prostaglandins, bradykinin, substance P, and other inflammatory mediators sensitize these receptors, lowering their threshold for activation and making the area more sensitive to touch and pressure than it normally would be. This heightened sensitivity is protective. It makes you guard the injured area, avoid loading it, prevent further damage during the vulnerable period of initial repair. Pain, at least in the acute setting, is a guardian. It is the body's way of communicating. Be careful here. Something important is happening here, and it needs space, and loss of function serves a similar, complementary purpose. It enforces rest at the tissue level, an inflamed joint that you cannot bend fully, an inflamed throat that makes swallowing uncomfortable, an inflamed muscle that cannot contract at full strength. These are all forms of biological immobilization. enforcing the reduction of mechanical and physiological stress while repair work proceeds beneath the surface. Now, into this inflamed zone, immune cells begin to arrive in sequence. Neutrophils are usually first on the scene. These are a type of white blood cell, produced continuously in the bone marrow, and circulating in enormous numbers in the bloodstream at all times. They are drawn to the site of injury by chemical gradients, a process called chemotaxis, following the trail of inflammatory signaling molecules the way a traveler might follow a scent carried on the wind. Within hours of an injury, neutrophils begin arriving at the damaged site in large numbers, squeezing through the slightly loosened walls of local blood vessels, a process called diapedesis, and entering the tissue space directly. At the site, they perform several essential functions. They engulf and destroy debris from damaged and dying cells. They target any bacteria that may have entered through the break in the skin, consuming them through a process called phagocytosis. Literally, cell eating. They release enzymes and reactive oxygen species that help sterilize the wound environment, killing microorganisms and breaking down damaged tissue components. But neutrophils are not built for longevity. They're built for urgency. They work intensely. They die in significant numbers at the wound site, and the cellular debris from their activity, the spent neutrophils, the consumed bacteria, the digested tissue fragments, becomes part of what the next wave of immune responders must clear. Within a day or two, another type of immune cell begins arriving in increasing numbers. Macrophages. These are derived from a circulating blood cell type called monocytes, which migrate from the bloodstream into the tissue, and there undergo a transformation, enlarging, taking on new capabilities, becoming the macrophages that will serve as the primary orchestrators of what comes next. The word macrophage comes from the Greek for big eater, and that is precisely what they are. They engulf dead neutrophils. They consume cellular debris. They phagocytose bacteria that the neutrophils may have missed or only partially addressed. They are extraordinarily thorough cleanup cells, clearing the wound environment with a methodical efficiency that prepares the ground for rebuilding. But macrophages do something else that is arguably even more important than their cleanup function. They orchestrate the transition from the destructive, clearing phase of inflammation to the constructive, building phase of repair. They do this by changing the chemical signals they release. Early in the inflammatory response, macrophages release pro-inflammatory cytokines, molecules that sustain and amplify the inflammatory environment. But as the wound is cleared and the immediate threat is contained, macrophages shift their profile. They begin releasing different signals: growth factors that stimulate fibroblast activity, molecules that promote the formation of new blood vessels, anti-inflammatory signals that begin to quiet the response that has now served its purpose. This is why the idea that inflammation is simply bad and should always be suppressed is biologically incomplete. Inflammation is not an unfortunate side effect of injury. It is the first and necessary stage of a healing process. The chemicals released during inflammation are the very signals that direct the cells needed for repair to where they need to be. The increased blood flow brings oxygen and nutrients. The swelling brings immune cells and growth factors. Remove inflammation entirely from the equation, and the repair machinery loses its initial instruction set. This is not to say that chronic inflammation is harmless. It is not, when inflammation persists long beyond the time needed for acute repair, when it continues for weeks, months, or years in the absence of ongoing injury or infection. It can cause significant damage to tissues and organs. Chronic, unresolved inflammation is associated with cardiovascular disease, type 2 diabetes, certain autoimmune conditions, and various other serious health challenges. The distinction is important. Acute, time-limited inflammation is a necessary and beneficial process. Chronic, unresolved inflammation is a different state entirely, and the resolution of inflammation is, it turns out, as actively orchestrated as its initiation. The body produces specific lipid molecules, with names like resolvins, protectins, and marazins, whose job is specifically to actively turn off the inflammatory response once it has served its purpose. These are not simply the absence of inflammatory signals. They are positive, active resolution signals. Healing requires not only the initiation of the right processes at the right time, but their controlled and timely cessation, acute inflammation, a controlled and purposeful clearing. That prepares the ground for what comes next. And what comes next is where the actual rebuilding begins. Once the inflammatory phase has done its work, once the wound is sterilized, the debris is cleared, the threat is contained, the body shifts into what biologists call the proliferative phase of healing. This is where construction begins in earnest. This is where the cells that specialize in building new tissue arrive and begin their slow, methodical, remarkably coordinated work. Imagine the wound site now, somewhere between 2 days and a week after the original injury. The clot is still present, darker now, drier at the surface, forming the scab that you may be tempted to pick at, though the biology beneath it is still very much active. The inflammation has not ended entirely, but it is clearly resolving. The redness is fading, the swelling is diminishing, the pain is less acute, and beneath the surface, an entirely new population of cells is beginning to organize and move. Among the most important of these builders are cells called fibroblasts. Fibroblasts are found throughout the body's connective tissues, in the dermis of skin, in tendons, in ligaments, in the capsules surrounding organs, in the supportive matrix that fills the spaces between more specialized cells. They are elongated cells, somewhat spindle-shaped, and they are specialists in producing the structural proteins that give connective tissue its mechanical properties. The most important of these proteins, and the one that will become central to wound repair, is collagen. You have almost certainly heard of collagen. It appears prominently in the marketing of cosmetic products, dietary supplements, and skincare regimens, but it is worth understanding what it actually is at the biological level. Because collagen is not simply a beauty molecule. It is arguably the most structurally important protein in the entire human body, and it is the primary architectural material of wound repair. Collagen is a long, triple helical protein. 3 polypeptide chains wound around one another in a precise helical configuration, like a 3-stranded biological rope. These triple helices are then assembled into larger fibrils, which are further organized into fibers and fiber bundles. The result is a material with extraordinary tensile strength, the ability to resist being pulled apart, combined with some degree of flexibility. Skin, tendons, ligaments, the outer layers of blood vessels, the scaffolding of bone, and the matrix of cartilage all depend on collagen networks for their structural integrity. In the healing wound, fibroblasts are summoned by growth factors released by macrophages and platelets. Chemical messages that say, in effect, come here, this space needs filling, this structure needs rebuilding. Fibroblasts at the wound margins and in the surrounding tissue respond to these signals, beginning to migrate toward the wound, and once there, to produce and secrete collagen and other matrix proteins into the wound space. This process is gradual and continuous. Over days, then weeks, the density of collagen in the wound increases, and the mechanical strength of the healing tissue grows. At the same time, something equally essential is happening in the wound. New blood vessels are forming. This process is called angiogenesis, the sprouting of new capillaries from existing blood vessels, with tiny cellular extensions reaching into the wound space like the tendrils of a vine finding its way through new territory. These new vessels are critical because the growing repair tissue, with its multiplying fibroblasts and all their energy demands, needs a blood supply. Without angiogenesis, the cells doing the rebuilding would be unable to survive in the oxygen-depleted interior of the wound. The tissue that forms as fibroblasts deposit collagen and new blood vessels grow through it has a specific appearance and a specific name: granulation tissue. If you have ever carefully examined a healing perhaps after a deeper cut where the scab has partially separated. You may have noticed the slightly pink, bumpy, moist texture beneath. That is granulation tissue. It looks almost like tiny granules of red or pink material, which is where the name comes from. Those granules are the loops of new capillaries visible through the thin overlying tissue. Granulation tissue is highly vascular, rich in fibroblasts and immune cells, and it represents the active construction site of wound healing. And then comes another cellular event that is critical to the final closure of the wound: the migration of keratinocytes. Keratinocytes are the primary cells of the epidermis, the outermost layer of skin. They are densely packed, layered in a stratified architecture that provides the body's primary physical barrier against the external environment. In normal skin, keratinocytes divide in the deepest layer of the epidermis, push upward through the layers above them as they mature, and eventually reach the surface, where they are shed as the tiny flakes of dead skin that coat every surface we touch. When a wound disrupts the epidermis, the keratinocytes at the wound margins receive signals from the disrupted environment, including signals from the loss of contact with neighboring cells, signals from the exposed wound surface below, and chemical signals from the inflammatory and repair cells in the wound. And they change their behavior. These normally stationary cells begin to move. They flatten, extend cellular protrusions, and migrate across the granulation tissue, advancing from both edges of the wound toward the center, covering the wound surface like a slowly closing curtain. This process is called reepithelialization, and when the advancing fronts of keratinocytes from opposite sides of the wound eventually meet in the middle, when the wound surface is covered, and the cells reestablish contact with one another, the process of rebuilding the stratified, layered architecture of normal epidermis begins. The wound is, in a surface sense, closed, but closure is only the visible end of the proliferative phase. Beneath the surface, remodeling continues for months. Now, let us step back from the wound site for a moment and think about something foundational, where all these cells come from, because every fibroblast that migrates into the wound, every keratinocyte that covers it, every endothelial cell that builds a new capillary, all of these had to originate somewhere. And the answer involves one of the most fascinating categories of cells in all of biology: stem cells. Stem cells are cells that have not yet fully committed to a specific functional identity. They retain the capacity, under the right conditions, and in response to the right signals, to give rise to multiple different specialized cell types. In the skin, resident stem cell populations in the base of hair follicles, and in the deepest layers of the epidermis, contribute to wound repair by producing new keratinocytes. In the bone marrow, hematopoietic stem cells give rise to the full range of blood and immune cells, the neutrophils, macrophages, and lymphocytes that are essential to healing. In other tissues, various stem cell populations, more or less active, more or less well characterized, contribute to regeneration and repair. The biology of stem cells is an active, rapidly advancing, and genuinely complex area of research. What is clear is that stem cells play important roles in tissue maintenance and repair across many organ systems, and that their activity tends to decline with age, a fact with significant implications for healing in older individuals, which we will explore in a later chapter. What is also clear is that the regulation of stem cell behavior, what activates them, what signals direct their differentiation into specific cell types, how the wound environment communicates with them, involves layers of molecular complexity that scientists are still actively working to understand. The cellular machinery of repair is not a simple, linear process. It is a sequence of overlapping, interdependent, mutually regulated events. Each phase creates the conditions for the next. Each cell type responds to signals produced by the ones that came before it, and produces signals that direct the ones that come after. It is a biological relay race of extraordinary coordination, and like the best relay races, What matters is not only the speed of any individual runner, but the seamlessness of the handoffs between them. We have already met some members of the immune system in the context of wound healing. Neutrophils arriving at the injury site within hours, macrophages orchestrating the transition from inflammation to repair. But the immune system's role in the body is broader than any single wound, and its contribution to healing extends across nearly every tissue and nearly every circumstance of biological repair. It is worth stepping back and understanding the immune system more fully, because it is one of the most complex and most important systems in the entire body. The immune system has two broad divisions. Understanding the distinction between them is one of the most useful things someone new to biology can learn. One of those simple science explanations for beginners that illuminates an enormous amount of downstream biology. The first division is called the innate immune system. Innate means inborn. This arm of immunity is present from birth, requires no prior exposure to any specific pathogen, and does not improve with experience. It responds rapidly, within minutes to hours of detecting a threat, using a relatively limited repertoire of recognition mechanisms. When the innate immune system detects danger, it does not pause to identify exactly what kind of pathogen it is dealing with. It recognizes broad patterns, molecular signatures that are common to bacteria, viruses, damaged cells, and foreign material generally, and it responds forcefully and immediately. The inflammatory response we described in the previous chapter is largely an innate immune response. The neutrophils, the macrophages, the natural killer cells that arrive at the wound are innate immune cells. They do not carry specific memories of past infections. They do not produce targeted antibodies, but they arrive fast, and they act decisively, and in those first hours and days after an injury. Speed matters enormously. The second division is the adaptive immune system. Adaptive immunity is slower to develop. It takes days to build a full adaptive response to a new threat, but it is exquisitely specific, and crucially, it learns and remembers. When the adaptive immune system encounters a pathogen, it generates lymphocytes, specifically B cells and T cells, that are individually tailored to recognize specific molecular features of that particular pathogen. B cells, once activated, differentiate into plasma cells that produce antibodies, proteins shaped precisely to bind to specific structures on the surface of pathogens, or foreign molecules. These antibodies mark pathogens for destruction by other immune cells, block them from entering host cells, and trigger additional immune responses. T cells perform a range of different functions, depending on their subtype. Cytotoxic T cells directly eliminate cells that are infected with viruses, or have otherwise become abnormal. Helper T cells produce signaling molecules that coordinate the responses of B cells, macrophages, and other immune components. Regulatory T cells help suppress the immune response when it is no longer needed, preventing it from becoming excessive or self-directed. And after the infection resolves, a subset of both B and T lymphocytes persists as memory cells, long-lived immune cells that retain the molecular information needed to recognize that specific pathogen again. The next time that pathogen is encountered, the adaptive immune response is dramatically faster and stronger. The body already knows, at the cellular level, how to respond. This is the biological basis of acquired immunity. It is also the basis of vaccination, which works by introducing the immune system to a harmless version or component of a pathogen in order to generate memory, without the cost and risk of actual disease. In the context of wound healing, the adaptive immune system is less immediately prominent than the innate response. Wounds are typically a problem of bacterial contamination and tissue damage, rather than viral infection, and the innate system handles the early phases of most wound responses quite effectively, but the adaptive system remains important, particularly if a wound becomes infected with bacteria that evade innate immune clearance, or if the injury involves a viral component. What macrophages do, in the transition between clearing and building, deserves additional attention, because they are among the most remarkable cells. In the healing response, macrophages are not fixed in their behavior. They exist on a spectrum of functional states, and they can shift along that spectrum in response to signals from their environment. Early in the inflammatory response, macrophages adopt what researchers describe as a classically activated state. They are pro-inflammatory, highly phagocytic, releasing cytokines that amplify the immune response, and cytotoxic molecules that help clear the wound of bacteria and cellular debris. They are in this phase, fundamentally a clearing force, but as the wound progresses, as the bacterial load is reduced, and the tissue environment begins to shift, macrophages transition toward an alternatively activated state. In this state, they release different signals: growth factors that stimulate fibroblast proliferation, and collagen production, factors that promote angiogenesis, anti-inflammatory molecules that begin to quiet the response that initially brought them there. They transform from a clearing force into a building supervisor, the cells that bridge the destructive and constructive phases of repair. Understanding this macrophage transition is one of the most active areas of wound healing research, because disruptions in this transition appear to contribute to the development of chronic, non-healing wounds, a significant clinical problem, particularly in people with diabetes or vascular disease, where wounds can fail to progress from the inflammatory to the proliferative phase and instead become stuck in a cycle of chronic inflammation and tissue degradation. Beyond the wound, the immune system conducts a continuous, quiet patrol of every tissue in the body. Natural killer cells circulate and monitor for cells that display signs of viral infection or abnormal behavior. Dendritic cells, distributed throughout the body's surfaces and tissues, act as molecular scouts, sampling their local environment and carrying information about foreign antigens to the lymph nodes, where adaptive immune responses are initiated. Mast cells, stationed in tissues near blood vessels, respond to local signals of disturbance by releasing inflammatory mediators that amplify early immune responses. All of this ongoing immune activity is, in the most fundamental sense, a form of continuous healing maintenance, a constant monitoring for disruption, with standing readiness to respond. The immune system does not heal wounds in isolation, but without the immune system, healing as we know it would be impossible. Bone feels, to the touch, permanent. It is cold and hard and dense. It is what remains long after everything else is gone. And so it is easy to think of the skeleton as a fixed structure, a framework built once in childhood and maintained essentially unchanged throughout a life. But this impression, however intuitive, is biologically incorrect. Bone is living tissue. It is metabolically active. It is constantly being broken down in some places and rebuilt in others. A process called bone remodeling that continues throughout adult life and is responsible for maintaining bone density, repairing microscopic damage from everyday loading, and adapting bone architecture to changes in mechanical demand. The skeleton you have today is not the same one you had 10 years ago. Much of its mineral content and protein matrix has been replaced since then. And when a bone fractures, when the forces applied to it exceed what its structure can bear, and it breaks, the process of its healing is one of the most structurally impressive examples of biological reconstruction in the human body. Let us follow a fracture through its stages. The moment a bone breaks, the damage is not limited to the mineral matrix of the bone itself. The bone is enclosed in a membrane called the periosteum, a dense, fibrous, richly vascularized layer of connective tissue that adheres tightly to the outer bone surface. The periosteum contains populations of osteogenic cells, cells capable of producing new bone, and it plays a critical role in healing. Blood vessels running through the interior of the bone, through a network of microscopic channels called the Haversian system, are also disrupted at the fracture site. Blood from these vessels, and from vessels in the periosteum and surrounding soft tissues, floods the fracture gap. This blood collects and clots, forming what is called the fracture hematoma, unlike a superficial skin wound clot, whose primary function is to stop bleeding and form a temporary barrier. The fracture hematoma serves as the initial biological scaffold for the entire bone healing process. It fills the gap between the broken ends, provides a matrix into which repair cells can migrate, and releases a complex of signaling molecules, from platelets, from the damaged bone cells themselves, from inflammatory cells arriving at the site, that initiate the subsequent healing stages. Inflammation follows, as it does with any significant tissue injury. Immune cells arrive, debris is cleared, and a rich signaling environment is established. Within this environment, over the course of the first week or two, the fracture hematoma is gradually transformed into what is called a soft callus. The soft callus is composed primarily of cartilage, the same semi-flexible connective tissue that cushions the surfaces of joints. Cartilage forms faster than bone and can bridge the fracture gap relatively quickly, providing mechanical stabilization and a structural template for the mineralization that follows. The cells that produce the cartilage, chondroblasts, are recruited from the periosteum and from local stem cell populations, guided to the fracture site by the growth factors and inflammatory signals present there. Over the following weeks, the soft cartilaginous callus undergoes a remarkable transformation. Mineral deposits, primarily in the form of calcium phosphate crystals called hydroxyapatite, the same mineral that makes up the inorganic component of normal bone, begin to be deposited within the cartilage matrix. The cartilage gradually converts to bone through a process called endochondral ossification, the same process by which most bones in the body formed originally during fetal development. The soft, flexible callus becomes a hard callus, calcified, rigid, substantially stronger than the cartilage it replaced. The hard callus is not yet normal bone. It is larger than the original bone. It must be, to bridge the gap and provide generous mechanical reinforcement around the fracture site. And it is less organized than mature lamellar bone, but it is strong enough for weight-bearing and load-resisting. It provides the structural stability needed for daily function, while the much slower process of remodeling begins. Remodeling is the final stage of bone healing, and it is the longest. It can continue for months to years after the fracture, gradually replacing the disorganized hard callus with the organized, architecturally efficient structure of mature bone. This remodeling is carried out by the two cell types that govern bone turnover throughout adult life: osteoblasts and osteoclasts. Osteoblasts are bone-forming cells, derived from progenitor populations in the periosteum and bone marrow. They synthesize and deposit the collagen matrix and mineral that comprise new bone tissue. They build in layers, producing the concentric rings of organized lamellar bone that give mature bone its characteristic microscopic architecture and its remarkable combination of strength and weight efficiency. Osteoclasts are bone-resorbing cells, large, multinucleated cells that dissolve both the mineral and protein components of bone by secreting acids and enzymes onto the bone surface. Their role is to remove old, disorganized, or mechanically inferior bone, to make way for the organized structure that osteoblasts will build in its place. Together, in coordinated teams, osteoclasts tunneling through old callus tissue, osteoblasts laying down new organized bone behind them. These cells gradually convert the fracture callus into bone that increasingly resembles the original in its structure. The large bump of callus visible on an X-ray shortly after a fracture will, given enough time, reduce. The bone architecture will be refined, and in many cases, the healed bone will be mechanically indistinguishable from, or stronger than, the bone that existed before the fracture. The remodeling is shaped by the mechanical forces applied to the bone, the loading patterns from weight-bearing and movement that signal, through complex mechanosensory mechanisms, where bone is most needed, and in what orientation its fibers should run. This is why rehabilitation that includes appropriate weight bearing after fracture, under medical guidance, is generally important. The biological signal of mechanical load is part of the instruction set that guides the remodeling process toward optimal architecture. Bone healing is a slow process. It is not glamorous, it is not visible, but it is a sustained, systematic, biologically extraordinary reconstruction. The body reassembling something as architecturally complex as mature bone, from nothing more than a blood clot and a set of molecular signals. The brain was, for most of the 20th century, considered to be essentially fixed in structure by adulthood. The prevailing view held that neurons, the electrically active nerve cells of the brain and spinal cord, could not regenerate after death, and that the circuit architecture of the adult brain was more or less permanently established sometime in early adulthood. The brain you had at 25, this view implied, was the brain you would inhabit for the rest of your life, gradually declining from that point on. This view has been substantially and importantly revised over the past several decades. Not overturned entirely, some of the observations that supported it remain valid, but complicated, nuanced, and expanded by a body of research that has revealed a brain considerably more changeable and adaptable than the old model allowed. The concept at the center of this revision is neuroplasticity. Neuroplasticity refers to the brain's capacity to modify its own structure and function in response to experience, learning, injury, and recovery. It encompasses changes at multiple scales, from the molecular changes at individual synapses that underlie memory and learning, to the large-scale reorganization of functional brain regions that can occur after injury. It is not unlimited. It is not equally powerful at all ages or in all circumstances. But it is real, it is pervasive, and it is one of the most important properties that the brain brings to the process of healing. To understand neuroplasticity, we need to understand something about how the brain communicates with itself. The brain contains approximately 86 billion neurons, each of which may form thousands of synaptic connections with other neurons. At each synapse, electrical signals in one neuron trigger the release of chemical messengers called neurotransmitters, which diffuse across the tiny synaptic gap and bind to receptors on the receiving neuron, either exciting or inhibiting its activity. The brain's function, every thought, perception, memory, emotion, and movement, emerges from the patterns of activity across this vast network of connected neurons. The critical insight of neuroplasticity research is that the strength of synaptic connections is not fixed. Connections that are repeatedly and reliably activated together tend to strengthen. The receiving neuron becomes more sensitive to input from the transmitting neuron, and the transmission itself becomes more efficient. Connections that are rarely or inconsistently activated tend to weaken and eventually be pruned. This principle, sometimes summarized as neurons that fire together wire together, is the cellular foundation of learning and memory. When you practice a skill, a piano scale, a tennis serve, the pronunciation of a word in a new language, the repeated activation of the neural circuits that support that skill gradually reshapes those circuits at the synaptic level. Connections become stronger. Transmission becomes faster. The pathway becomes, in a biological sense, more worn, like a path through grass that becomes more visible and easier to walk with each passage. The skill becomes more automatic because the neural architecture supporting it has been physically modified by practice. This same mechanism is what allows the brain to recover, to varying degrees, after injury. When a stroke cuts off blood supply to a region of the brain, depriving its neurons of oxygen and glucose until they die, the functions that region supported are lost. Motor control, language, vision, sensation, or cognition may be impaired depending on which region is affected. And unlike skin cells or bone cells, neurons in the central nervous system do not regenerate. The cells that die are not replaced by new neurons. And yet, with time and intensive rehabilitation, many people recover significant function after stroke. Some recover remarkable amounts of function. not because the dead neurons have returned, but because the brain reorganizes around the loss. What research suggests happens during stroke rehabilitation is that the intensive, repeated practice of impaired functions, relearning to move a limb, relearning to form words, relearning to sequence movements, drives sustained neural activity in regions of the brain adjacent to, or elsewhere connected with, the damaged zone. Over time, through the same mechanisms of synaptic strengthening that underlie ordinary learning, these undamaged regions develop stronger connections to the downstream pathways that the stroke-damaged area previously served. They gradually take on some of the lost function. This is adaptation rather than restoration. The brain that recovers from stroke is not the same brain as before the stroke. It has reorganized. The function is served by different neural real estate, different pathways, different circuits. But the function may, in favorable cases, be substantially recovered, and that recovery reflects the plastic capacity of the surviving brain tissue. The extent of this recovery varies enormously. It depends on the size and location of the stroke, the age of the person, the intensity and timing of rehabilitation, the health of the surrounding brain tissue, and factors that researchers are still working to fully characterize. Not all strokes lead to meaningful recovery. For some, the damage is simply too extensive or too strategically placed for the surviving tissue to compensate adequately. But for many, neuroplasticity is the mechanism that makes recovery possible at all. Neuroplasticity is also at work every day, in every ordinary learning experience, every new memory formed, every habit built. The brain that recovers from injury and the brain that learns a language or masters a skill are not doing different things. They are doing the same thing, modifying their synaptic architecture in response to experience, just in different contexts and for different reasons. Learning is, in this biological sense, a daily, continuous, quiet form of neural cultivation. There is also the remarkable and still somewhat contested matter of neurogenesis, the actual production of new neurons in the adult brain. For decades, the consensus held that adult neurogenesis was essentially absent in mammals. Then research in the 1990s revealed clear evidence of ongoing neurogenesis in specific regions of the adult rodent brain, particularly in an area of the hippocampus called the dentate gyrus. Subsequent work in humans has found evidence consistent with some degree of adult neurogenesis in the hippocampus, though the extent and functional significance of human adult neurogenesis remains an area of active investigation and genuine scientific debate. What current evidence suggests with reasonable confidence is that some neurogenesis does occur in specific adult human brain regions, that it can be influenced by environmental and lifestyle factors. Physical exercise appears to be among the most robust stimulators, and that it may play roles in certain aspects of memory and mood. But this is not unlimited neural regeneration. It is a modest, region-specific, tightly regulated process, one piece of a complex picture. The brain heals differently from skin or bone. Its healing is not primarily about cellular replacement. It is about reorganization, compensation, and the cultivation of new pathways through the architecture that remains. It is, in many ways, the most philosophically interesting form of healing in the body, because it is the form of healing that most directly involves who we are, our memories, our abilities, our sense of self. We arrive now at something that occupies roughly a third of every human life, something the body pursues with such insistent urgency that prolonged deprivation of it produces cascading failures across virtually every biological system, and which we rarely, in our waking hours, think about in terms of its biology. Sleep, for most people, is simply what happens when the day is done. Rest, darkness, absence. The biology tells a fundamentally different story. Sleep is not the absence of biological activity. It is a distinct and active biological state, a mode of operation quite different from wakefulness in its chemistry, its neural patterns, its hormonal profile, and its priorities. And among the most important of its functions, perhaps some researchers argue, among the primary reasons sleep evolved in the first place, is the facilitation of biological repair. Let us trace what happens to the body as sleep begins. As wakefulness transitions into sleep, the brain shifts its electrical activity from the rapid, irregular patterns of conscious awareness to the slower, more rhythmic patterns of early sleep. The body temperature drops slightly, muscle tone decreases, the sensory systems reduce their thresholds, and the endocrine system, the hormonal communication network of the body, undergoes a significant shift. Among the most important of the hormonal changes of early sleep is the release of growth hormone from the anterior pituitary gland, a small but remarkably powerful structure at the base of the brain. Growth hormone is released in pulses throughout the day and night, but the largest and most reliable surge occurs in the first 1 to 2 hours of sleep, specifically during the first episodes of slow wave or deep sleep. This is not a coincidence of biology. It reflects the fundamental coupling between sleep architecture and the hormonal regulation of tissue repair. Growth hormone in adults does not primarily drive height increases. That role is largely complete by early adulthood. Instead, it performs a range of metabolic and reparative functions. Chief among these is the stimulation of protein synthesis, the production of new proteins, in cells throughout the body. Proteins are the molecular workhorses of biological function. Enzymes, structural proteins, signaling molecules, transporters. All of these are proteins, and all of them are continuously produced, used, damaged, and replaced. The rate at which the body can synthesize these replacement proteins depends significantly on the availability of growth hormone, and growth hormone surges during deep sleep. This is why sleep is so tightly connected to physical recovery. Muscle fibers sustain microscopic tears during exercise, and the repair and reinforcement of those fibers, the biological basis of the strength gains that follow training, depends on protein synthesis that is substantially amplified during sleep. Research has consistently found that sleep deprivation impairs protein synthesis rates, delays wound healing, and reduces the body's capacity to recover from physical stress. Athletes who prioritize sleep tend to recover faster and adapt more efficiently to training than those who do not. The immune system's relationship with sleep is bidirectional and profound. It is well established that illness drives sleepiness. Cytokines released during infection activate sleep-promoting pathways in the brain, increasing sleep duration and depth. This is not merely a symptom of illness. Research suggests it is a functional response that facilitates immune activity. During sleep, the production and activity of certain immune cells, particularly T cells and natural killer cells, appears to be enhanced. The concentration of various cytokines follows circadian and sleep-dependent patterns. The adaptive immune system's process of consolidating memories of encountered pathogens, making the immune memory more durable and effective, appears to be supported by sleep. An illuminating example comes from vaccination research. Multiple studies have found that sleep restriction in the days around vaccination significantly reduces the antibody response generated. The immune system's production of pathogen-specific antibodies is diminished when sleep is inadequate. The immune learning that vaccination depends on appears to require sleep for full consolidation, just as declarative learning requires sleep for memory consolidation. The brain has its own sleep-dependent repair and maintenance process, distinct from and complementary to the systemic hormonal effects described above. During wakefulness, neurons are metabolically active. They consume glucose, produce ADP, generate electrical signals. And this metabolic activity produces waste products, as all metabolism does. Among the most discussed of these waste products in recent research is beta amyloid, a protein fragment that accumulates in the brain over time and is associated, at elevated levels, with neurodegenerative disease. During sleep, and particularly during slow-wave sleep, a system called the glymphatic system becomes dramatically more active. The glymphatic system uses the flow of cerebrospinal fluid through channels surrounding cerebral blood vessels to wash through the interstitial spaces of the brain. During sleep, the spaces between brain cells appear to expand by as much as 60% compared to wakefulness, allowing cerebrospinal fluid to flow more freely and carry metabolic waste products, including beta amyloid and other solutes, out of the brain parenchyma and into the body's general waste clearance pathways. Sleep, in this specific mechanistic sense, cleans the brain. It is a nightly maintenance cycle, removing the molecular byproducts of a day of thinking. Memory consolidation during sleep is another form of neural maintenance. During wakefulness, learning involves the temporary strengthening of synaptic connections that encode the information acquired during the day. But this encoding is initially labile, vulnerable to interference, not yet fully integrated into the long-term memory architecture. During sleep, and through processes that involve both slow-wave sleep and REM sleep in different ways, these newly encoded memories are replayed, processed, and consolidated, strengthened, and integrated into existing long-term memory networks. Slow-wave sleep appears particularly important for declarative memories, the memories of facts and events. REM sleep appears important for procedural memories and for the emotional processing of memories. This consolidation is not passive storage. It is active reorganization. The brain deciding, in some biological sense it does not yet fully understand, which of the day's experiences are worth keeping, how they relate to what is already known, and how they should be integrated into the larger architecture of what one knows. Sleep, viewed from all these perspectives, is not rest. It is a carefully orchestrated biological program of maintenance, repair, immune calibration, metabolic waste clearance, and neural reorganization. A program that cannot be deferred indefinitely without serious biological consequence. The body insists on it, and now we understand, at least in part, why. There is a molecule, a steroid hormone, to be precise, whose reputation in popular health discussion has become almost entirely negative. It is cortisol, and it is blamed, with what has become something of a cultural fervor, for weight gain, sleep disruption, immune suppression, skin problems, cardiovascular disease, premature aging, and a long list of other conditions. Like inflammation before it, cortisol has been cast as the villain of the body's own biochemistry, something to be minimized, suppressed, and worried about. Like inflammation before it, this characterization is incomplete. Cortisol is a glucocorticoid steroid hormone produced by the adrenal cortex, the outer layer of the adrenal glands, which sit like small caps atop each kidney. Its production is regulated by the hypothalamic pituitary adrenal axis, or HPA axis, a feedback loop involving the hypothalamus in the brain, the pituitary gland at the brain's base, and the adrenal glands themselves. When the hypothalamus detects a stressor, whether physical, psychological, or metabolic, it releases a signal to the pituitary, which releases ACTH, adrenocorticotropic hormone, into the bloodstream, which travels to the adrenal glands and stimulates the production and release of cortisol. In the short term, cortisol does exactly what it is designed to do, and it does it well. It mobilizes energy reserves, stimulating the release of glucose from storage and the breakdown of proteins and fats to provide additional metabolic fuel. It sharpens attention and increases alertness. It modulates immune activity, temporarily suppressing some aspects of immune function that would be metabolically costly and are not urgently needed in the short term. It prepares, in short, the body for action, for the kind of immediate physical challenge that the stress response evolved to handle. The morning cortisol awakening response, the natural surge of cortisol in the first hour after waking, is not a sign of pathological stress. It is a normal and necessary physiological primer for the day, priming the metabolism and the alertness systems for the demands ahead. Cortisol is not something the body produces by mistake. It is something the body produces on purpose, for good biological reasons. The problem arises not from cortisol itself, but from chronically elevated cortisol, the sustained, prolonged HPA axis activation that occurs when psychosocial stressors persist without resolution. When the stress response is triggered repeatedly and the turning off mechanisms are insufficiently engaged. When cortisol levels remain high for weeks or months rather than hours. The downstream consequences for biological function, including healing, are significant. Chronically elevated cortisol suppresses the production of certain pro-inflammatory cytokines, the very signaling molecules that initiate the acute inflammatory response necessary for wound healing. It impairs the migration of immune cells to wound sites. It reduces the production and release of growth hormone, thereby diminishing the protein synthesis upon which tissue repair depends. It affects the function of fibroblasts, the collagen-producing cells we met in an earlier chapter, in ways that can reduce the efficiency of connective tissue repair. It disrupts sleep architecture, reducing the amount of slow-wave deep sleep and the growth hormone surges that accompany it. The evidence for stress-impaired wound healing is perhaps best illustrated by a set of studies that examined healing rates in people experiencing prolonged psychological stress. Caregivers of family members with serious illness, a group that reliably shows physiological markers of chronic stress activation, have been found in multiple studies to heal experimental wounds more slowly than matched non-caregiver controls. The impairment is not dramatic, but it is consistent and measurable. The stress response, sustained over time, reaches into the cellular biology of repair and makes it less efficient. This matters, but it must be held carefully. The relationship between psychological state and healing is real, but it is not simple or linear, and it is easy to misrepresent in ways that are not helpful and not accurate. Not all stress impairs healing. Brief, acute stressors may actually have modest stimulating effects on certain immune functions. The evidence for stress-impaired healing is most robust for severe, chronic, unresolved stress, not for the ordinary pressures and demands of a typical day. And the mechanisms through which psychological states affect physiology are indirect, operating through hormonal and neural pathways that modulate the broader biological environment rather than directly controlling cellular repair. What biology can honestly say is this: prolonged, unresolved psychological stress creates a systemic hormonal and immune environment that is somewhat less conducive to efficient healing than the resting state. Interventions that reduce chronic HPA axis activation, whether through improved sleep, social connection, physical activity, professional psychological support, or changes in stressful circumstances, may, through these biological pathways, be modestly supportive of healing processes. This is a measured, careful statement. It is not a claim that thinking positive thoughts heals wounds, or that all illness is psychosomatic, or that the mind alone determines the body's repair capacity. It is a statement that the body's systems are interconnected, that the neural, endocrine, and immune systems communicate constantly and bidirectionally, and that the state of one influences the state of the others. This interconnection is not mystical. It is anatomical. It is molecular. It is physiology. It is important to speak about psychological and emotional healing with both precision and care, because this territory is easily distorted, both by the tendency to reduce it entirely to the biological, and by the tendency to treat it as purely subjective and beyond biological description. The truth, as current science understands it, lies in holding both levels simultaneously. Emotional healing is a deeply personal, individual, subjective experience, and it is simultaneously a set of biological processes occurring in neural tissue, hormonal systems, and autonomic pathways. Emotional pain is real. Trauma is real. The suffering that follows loss, violation, grief, chronic fear, or sustained helplessness is not less real for being invisible. And the healing of psychological wounds, however incomplete that healing may sometimes be, involves changes in the brain that are, at the cellular and molecular level, as concrete as the changes that heal a wound in skin. When something deeply frightening or distressing happens, the brain responds with remarkable speed. The amygdala, a pair of almond-shaped structures deep in the temporal lobes, central to the processing of emotional salience and threat, activates immediately. It does not wait for conscious evaluation. It responds to the emotional and sensory features of the experience before the slower, more analytical prefrontal cortex has finished processing them. The amygdala sends signals that trigger the HPA axis and the sympathetic nervous system, initiating the stress response. Heart rate accelerates, breathing quickens and shallows, blood is shunted toward muscles, attention narrows. The body has mobilized for threat. In an acute, time-limited threat that resolves, this response also resolves. The prefrontal cortex, which modulates amygdala activity through inhibitory connections, reasserts its regulatory influence. The parasympathetic nervous system, the rest and digest counterpart to the fight or flight system, reasserts its tone. Cortisol levels fall. Heart rate slows. The acute stress response concludes. But in cases of severe trauma, particularly repeated, inescapable, or unpredictable threat, this resolution does not proceed normally. The memory of the threatening experience is encoded with unusual strength. Emotional memories are, according to current neuroscience, consolidated differently from neutral memories. The amygdala modulates the consolidation of memories in the hippocampus, the memory-forming region of the brain, and strong emotional activation enhances this modulation. Memories formed in the context of intense emotional arousal tend to be more vivid, more durable, more easily triggered, and more resistant to the normal forgetting that gradually attenuates neutral memories over time. This has evolutionary logic. Memories of serious danger are important to retain because they may help avoid similar danger in the future. But it also means that traumatic memories can be unusually intrusive, unusually difficult to contextualize within the broader narrative of one's experience, and unusually powerful in their ability to trigger physiological stress responses long after the original threat has passed. In conditions like post-traumatic stress disorder, the normal regulatory mechanisms appear to be disrupted in specific ways. The prefrontal cortex's capacity to modulate amygdala reactivity is reduced. Traumatic memories trigger responses disproportionate to the current context. The nervous system is, in a very concrete biological sense, stuck in a state of heightened readiness, as though the threat remains present even when it does not. Recovery from this state involves, among other things, a biological process called memory reconsolidation. Each time a memory is retrieved, recalled from long-term storage into active awareness, it returns temporarily to a label, modifiable state before being restored. This reconsolidation window offers an opportunity, in principle, for the memory to be updated, not erased, but modified. New contextual information can be integrated. The emotional intensity associated with the memory can potentially be reduced. This is believed to be part of the mechanism underlying several evidence-based therapeutic approaches to trauma, though the clinical application of reconsolidation science is still a developing field. The social environment is also biologically significant in emotional healing. The experience of genuine connection with another person, of feeling seen, understood, and safe in the presence of another, has measurable physiological effects. The release of oxytocin, a neuropeptide produced in the hypothalamus and released from the posterior pituitary, is associated with social bonding and with experiences of trust and safety. Oxytocin appears to reduce amygdala reactivity. It modulates the threat detection system, reducing its hypersensitivity. It also appears to reduce cortisol levels and support the tone of the parasympathetic nervous system. Research suggests that social support, the experience of having reliable, responsive, caring relationships, is associated with measurable differences in physiological stress responses, in inflammatory markers, and in recovery from both physical and psychological challenges. The mechanism is not fully characterized, but the association is consistent and has been replicated across multiple study designs and populations. The nervous system's recovery from trauma moves gradually, with appropriate support and time, toward what researchers describe as regulation. The capacity to experience strong emotions without being overwhelmed by them, to return to physiological baseline after stress, to engage flexibly with difficult material rather than avoiding or being engulfed by it. This regulation is not simply willpower or positive thinking. It is a biological achievement, the result of gradual changes in neural circuitry, in the balance between prefrontal regulatory capacity and amygdala reactivity, in the calibration of the HPA axis. This is educational context, not clinical guidance. Serious psychological trauma and its treatment are complex and require qualified professional support. But the central point holds. Emotional healing is not a metaphor. At the level of neurons, synapses, hormones, and autonomic tone, it is as real and as biological as any other form of healing. It is simply the form of healing that is most profoundly shaped by experience, relationship, and the long arc of time. Every scar is a record, a quiet, permanent notation in the tissue, marking the place where something went wrong, and the body responded, not with perfect restoration, because perfect restoration is not always what biology provides, but with the most efficient, most reliable repair it could manage under the circumstances. A scar is evidence of repair that did not achieve regeneration. It is biology's pragmatic compromise, the outcome of a healing process that prioritized closure and structural integrity over the full recreation of original tissue complexity. Understanding why scars form, and why they look and feel the way they do, reveals something important about the nature and priorities of healing itself. When a wound is repaired, the primary biological imperative is speed. An open wound is a portal of entry for pathogens. It is a site of fluid loss. It is a structural weakness in the body's primary barrier. The longer it remains open, the greater the risk of infection, and the greater the ongoing cost to the body. Evolution has therefore shaped the repair process to prioritize rapid closure above architectural perfection. Fibroblasts responding to wound healing signals lay down collagen rapidly, but the collagen they produce under the urgency of wound healing is organized differently from the collagen of normal, undamaged dermis. In normal skin, collagen fibers are arranged in a basket weave pattern, interwoven at multiple angles, providing strength in multiple directions, and maintaining the skin's resilience and elasticity. In scar tissue, the collagen fibers tend to be more parallel, more uniform in their orientation, more densely packed. This parallel arrangement is mechanically strong enough to close and hold the wound, but it lacks the multi-directional resilience of normal skin. Scar tissue also lacks many of the specialized structures that normal skin contains. Hair follicles, which derive from complex epithelial and mesenchymal interactions during development, do not regenerate in scar tissue, which is why scars are characteristically hairless. Sweat glands and sebaceous glands, similarly complex in their architecture, do not regenerate. Melanocytes, the pigment-producing cells that give skin its color, may be absent or distributed abnormally in scar tissue, which is why scars are often lighter or darker than the surrounding skin. The sensory nerve network that gives normal skin its fine-grained tactile sensitivity may be reduced or differently arranged in scar tissue. None of this represents a failure of the healing process. It represents the healing process being honest about its priorities. Speed and closure, in evolutionary terms, outweigh structural perfection, because an animal that rapidly closes its wounds survives long enough to heal imperfectly, while one that heals perfectly but slowly may not survive the infection that enters during the delay. There is considerable variation in scarring between individuals, and between different wounds in the same individual. Wounds that close easily and quickly, small incisions under minimal tension, in areas with good blood supply, tend to produce less prominent scars. Wounds under tension, wounds in areas of limited blood supply, wounds that become infected and sustain prolonged inflammatory activity, and wounds left to heal without edges being approximated, tend to produce more prominent scarring. The inflammatory environment directly influences fibroblast behavior. Higher levels of inflammatory signaling tend to drive more rapid and less organized collagen deposition. Some individuals are prone to excessive scar formation. Hypertrophic scars are raised and thickened scars that remain within the boundaries of the original wound. They are the body producing too much collagen in repair, creating a scar more prominent than the wound would strictly require. Keloid scars are an extreme version of this tendency. in which scar tissue grows beyond the boundaries of the original wound, sometimes considerably so, forming raised, firm, sometimes pruritic growths. That can be both cosmetically significant and physically uncomfortable. Keloid formation has a clear genetic component, appears to be more prevalent in individuals of African or Asian ancestry, and the precise molecular basis of why some individuals' fibroblasts behave this way is an ongoing area of research. Fetal wound healing offers a striking contrast to adult healing, and a potential biological lesson. Wounds sustained during fetal development, in the early to mid-gestational period, heal without scars. Fetal skin regenerates. The architectural complexity of the original tissue is restored. The reasons for this are not entirely understood, but research points to differences in the composition of the extracellular matrix environment in fetal tissue, differences in the character of the fetal inflammatory response, and differences in the growth factor signaling that fibroblasts receive. Scientists studying fetal healing hope that understanding these molecular differences might eventually point toward ways to reduce or prevent scarring in adult wound repair. A scar is not a wound that failed to heal. It is a wound that healed in a particular way, the most efficient way available to it. Every scar is evidence of a crisis met and contained, a barrier restored, a biological problem resolved. The mark it leaves is the record of that resolution. Age is not merely the accumulation of time. It is the accumulation of biological change, molecular, cellular, tissue level, and systemic changes that alter the body's capabilities in ways that are, at this point in scientific understanding, largely inevitable, though their pace and character are influenced by many factors. Among the capabilities that change most clearly with age is the ability to heal. Most people who reach middle age and beyond have noticed this directly. A cut that would have sealed in days now takes a week. A bruise that would have faded in a week now persists for 2. A muscle strain lingers past its expected resolution. Recovery from illness is slower, more effortful, more draining. These observations are not imagination or hypochondria. They reflect real biological changes in the efficiency of repair at every level. At the cellular level, perhaps the most significant age-related change for healing is the progressive decline in stem cell activity across most tissues. Stem cells are the source of replacement cells in tissue repair, the populations from which new keratinocytes, new fibroblasts, new blood cells, new bone-forming cells are ultimately derived. In young tissues, these populations are robust and responsive, quickly activated by injury signals, efficiently producing differentiated progeny that can do the work of repair. With age, stem cell populations in many tissues decline in number, in responsiveness, and in the quality of their output. They divide more slowly. They may differentiate less faithfully. They respond to injury signals less vigorously. In the skin, this manifests as slower reepithelialization after wounding, reduced collagen synthesis by aging fibroblasts, thinner and less elastic dermis, and less efficient closure of wounds. In bone, it manifests as reduced osteogenic activity in the periosteum and bone marrow, slower callus formation, less efficient remodeling, fractures that take longer to reach mechanical stability, and may never achieve the same degree of architectural refinement as fractures in young bone. The immune system undergoes a well-documented set of age-related changes, collectively described as immunosenescence, the progressive decline in immune competence with advancing age, the production of naive T cells, capable of responding to novel antigens, declines substantially as the thymus, the organ where T cells mature, involutes with age. Antibody responses to vaccines and infections tend to be weaker and shorter-lived in older individuals. Natural killer cell activity may be reduced. The overall capacity to mount vigorous, well-coordinated immune responses to challenge decreases simultaneously, and this is one of the most interesting paradoxes of immunosenescence. Older individuals tend to have elevated levels of baseline inflammatory markers, C-reactive protein, interleukin-6, and other indices of systemic inflammation tend to rise with age, even in the absence of obvious infection or injury. This phenomenon, labeled inflammaging in the scientific literature, reflects a kind of persistent, low-grade, nonspecific inflammatory state that appears to develop as part of normal aging and is associated with many age-related diseases. The aging immune system, in other words, is simultaneously less capable of specific, targeted responses and more inclined toward nonspecific background inflammation, a combination that is in several respects the worst of both worlds for efficient healing. The hormonal environment changes significantly with age, in ways that directly affect repair capacity. Growth hormone secretion declines substantially in older adults. The large pulses that accompany deep sleep become smaller and less frequent, since growth hormone drives the protein synthesis that underlies tissue repair. Its decline contributes directly to the slowing of cellular maintenance processes. Estrogen, which in premenopausal women supports collagen synthesis, skin thickness, wound healing, and the balance of osteoblast and osteoclast activity, declines at menopause, with significant consequences for skin repair and bone health. Testosterone declines in older men, with implications for muscle maintenance, and through muscle's role in metabolism and mobility, indirect consequences for healing capacity. At the molecular level, the phenomenon of cellular senescence, cells that have stopped dividing and entered a state of permanent growth arrest, often because their telomeres have shortened to a critical length after many divisions, becomes increasingly relevant with age. Senescent cells accumulate in many tissues as the body ages. They are not simply inactive. They adopt what researchers call the senescence-associated secretory phenotype, releasing a complex of pro-inflammatory cytokines, proteases, and other bioactive molecules that alter the local tissue environment. This secretory activity appears to contribute to the chronic low-grade inflammation of aging, to impairments in stem cell function, and to various aspects of age-related tissue dysfunction. Understanding the biology of aging and healing is not simply an academic exercise. It has direct implications for a rapidly aging global population, facing an increasing burden of age-associated conditions, in which impaired healing of wounds, of bones, of the vasculature, plays a significant clinical role. The pace of research into the biology of aging has accelerated considerably in recent years, and the understanding of what drives these changes and what might slow or modify them is advancing. One of the most important things that honest science does is hold wonder and limitation in the same hand. It does not look away from either. It does not exaggerate what is possible, and it does not understate what is remarkable. And when it comes to healing, the honest accounting includes both. The body is extraordinarily capable, but it is not omnipotent. Some tissues, after certain kinds of damage, do not fully recover. Some functions, once lost, are not restored by biology alone. Some wounds leave permanent marks, not just at the surface, but deep in the architecture of organs and systems. Understanding where these limits lie, and why, is part of understanding what healing is. The central nervous system presents some of the most profound limits to healing biology. The neurons of the brain and spinal cord are, as we have discussed, among the most limited cells in the human body when it comes to self-renewal. When they die, whether from ischemia in a stroke, from physical trauma, from the pressure of a tumor, or from the progressive damage of neurodegenerative disease, they are not replaced by new neurons. The brain compensates through neuroplasticity, as we have explored, but this compensation has its own limits. Large strokes or severe traumatic brain injuries may exceed what reorganization can compensate for, leaving permanent functional deficits. In the spinal cord, the situation is in some respects even more constrained. Not only do spinal cord neurons not regenerate after injury, but the environment of the adult central nervous system is actively inhibitory to nerve fiber regrowth. The glial scar that forms at a spinal cord injury site, a reaction that serves certain protective functions by containing the damage, contains molecules that actively repel the growth of regenerating axons. The result is that complete spinal cord injuries, those that fully sever the cord at a given level, result in permanent loss of motor and sensory function below that level. In the vast majority of cases, this is one of the most painful limits in all of clinical medicine, and it drives enormous research investment worldwide into strategies to overcome the inhibitory environment of the injured spinal cord and permit meaningful regeneration. Partial spinal cord injuries are more variable in their outcomes, and some recovery of function is possible in these cases, reflecting the contribution of surviving, undamaged axons, and some degree of neuroplastic reorganization. But complete regeneration of a fully severed spinal cord is not something that current biology can achieve on its own. The heart presents a different, but equally significant limit. The cardiomyocytes, the contractile cells that make up the heart muscle, have extremely limited regenerative capacity in the adult human heart. Research has estimated that less than 1% of cardiomyocytes are replaced per year in young adults, and this rate declines with age. When a heart attack kills a significant population of cardiomyocytes, by cutting off their blood supply, those cells are not replaced by new cardiomyocytes. They are replaced by fibrous scar tissue, produced by cardiac fibroblasts responding to the damaged signals of the infarct zone. This scar is mechanically sufficient to maintain the structural integrity of the heart wall, but it does not contract. It does not pump. The pumping capacity of the heart is permanently reduced in proportion to the mass of muscle that was lost. In contrast, the liver possesses remarkable regenerative capacity, a fact that has been exploited clinically in living donor liver transplantation. The liver can regenerate substantially, from as little as a quarter or a third of its original mass, restoring functional volume through the rapid proliferation of surviving hepatocytes. The mechanisms underlying hepatic regeneration are an active area of study and represent one of the most impressive examples of regenerative capacity. In the adult human body, articular cartilage, the smooth, low-friction tissue covering the surfaces of joints, is another tissue with limited healing capacity. Its avascular nature means that the cellular machinery of repair has no direct blood supply through which to receive its inputs. When cartilage is damaged, whether through acute injury or through the progressive wear of osteoarthritis, the repair that occurs is typically incomplete, producing fibrocartilage rather than the organized, mechanically superior hyaline cartilage of the original. This is why cartilage injuries are persistent, and why osteoarthritis, once established, tends to progress rather than reverse. These limits are not failures of design in any absolute sense. They reflect evolutionary trade-offs, the specific biology of each tissue type, the energy costs of different repair strategies, the mechanical and structural demands different tissues face. But they are real limits, and acknowledging them is part of taking the science of healing seriously. It is worth pausing here, in this exploration of the body's own capacities, to consider the role of medicine, and to think carefully about what medicine actually does in relation to biological healing. Because the relationship is not what popular narratives sometimes suggest. Medicine does not heal. The body heals. What medicine does, at its best, is understand the body's healing processes deeply enough to create the conditions under which those processes can work most efficiently, or to support and augment them when they are insufficient on their own. This is not a diminishment of medicine. It is, in many ways, the most respectful possible description of it. The idea that the highest form of medical practice is one that works in alignment with biology rather than around it. Surgery provides perhaps the clearest illustration. A surgeon performing wound closure is not healing the wound. They are approximating the edges with precision, minimizing the distance that migrating keratinocytes must travel, reducing the volume of granulation tissue that must be produced, decreasing the exposure to contamination. They are creating the optimal geometric and mechanical conditions for the body's own repair processes to proceed efficiently. The surgery is the setup. The biology is the execution. A surgeon placing a metal plate and screws across a complex fracture is similarly not healing the bone. They are restoring and maintaining the alignment of the broken fragments, providing mechanical stability so that the fracture hematoma can form properly, so that the callus can develop without being repeatedly disrupted by movement of the broken ends, so that the osteoblasts and osteoclasts can conduct their remodeling work in an environment that will produce functional architecture. Remove the biology, and the hardware is just metal. The hardware works because the biology works. Antibiotics operate on a different principle, but the underlying logic is the same. Antibiotics do not repair infected tissue. They reduce or eliminate the bacterial population, that is, maintaining the inflammatory phase of the wound, preventing the transition to the proliferative phase, and consuming resources that would otherwise be available for repair. They remove an obstacle. Once the bacteria are controlled or cleared, the body's wound healing cascade, which has been ongoing, however inefficiently, throughout the infection, can proceed more normally. Vaccination is perhaps the most philosophically interesting example. Vaccination does not provide immunity directly. It cannot. Immunity is the product of the adaptive immune system's learning, the generation of specific memory B and T cells that will recognize a pathogen and mount a rapid, vigorous response upon future encounter. The vaccine provides the learning stimulus, the antigen, or the information equivalent of the antigen, in a form that the immune system can respond to without the risk of actual disease. The immune system provides the response. The immunity generated is entirely built by the body's own biological machinery. The vaccine is the teacher. The immune system does the learning. Physical therapy, in the rehabilitation context, leverages the same neural plasticity and mechanical signaling we have discussed throughout this exploration. The therapist does not rebuild the damaged tissue or rewire the injured brain. They guide the biological process, providing the structured, progressive, specific mechanical and neural inputs that the biology of healing needs to proceed optimally. The loading of healing connective tissue that drives organized collagen remodeling, the repetitive movement practice that drives cortical reorganization after stroke, the carefully progressed exercise that maintains muscle mass and joint mobility during bone healing recovery. All of these are applications of biological knowledge to the management of biological processes. This collaborative model, medicine providing the conditions and the inputs that allow biology to do its work, is not a new idea, but it has become more explicitly articulated as the biological understanding of healing has deepened, and it has important implications. It suggests that the most effective medicine is the medicine that most deeply understands biology, and that medical interventions assessed by whether they genuinely support the body's repair processes, rather than merely suppressing symptoms or modifying measurements, are the interventions most likely to be truly beneficial. The science of healing is not finished. It is not close to finished. It is, in some of its most important dimensions, barely begun. The past century of biological and medical research has produced extraordinary advances in understanding, advances that have transformed the treatment of wounds, infections, fractures, neurological injuries, and immune disorders. But the distance between where understanding stands today and the ability to fully guide, augment, or replace the healing process remains vast. What lies ahead? The directions that researchers are currently exploring, the technologies that are beginning to show early promise, is worth considering carefully and honestly, without overpromising and without dismissing. Regenerative medicine represents perhaps the most ambitious horizon. As a field, It aims to do what the body cannot fully do on its own in many circumstances: to restore or replace damaged and lost tissues using biological materials and principles. It encompasses stem cell therapies, tissue engineering, gene therapy approaches, and the use of biological scaffolds and growth factor delivery systems to guide and enhance the body's native repair responses. Stem cell therapy has attracted enormous attention, enormous investment, and enormous amounts of premature enthusiasm, as well as, unfortunately, an ecosystem of unproven and sometimes dangerous clinics, offering treatments with no credible evidence base to vulnerable patients seeking cures for serious conditions. It is important to distinguish between what current evidence actually supports established therapies like hematopoietic stem cell transplantation for blood disorders, and carefully conducted ongoing clinical trials for various applications, and what remains speculative or insufficiently proven. Research into stem cell applications for cardiac repair, spinal cord injury, neurological diseases, and orthopedic conditions is active and, in some cases, genuinely promising. But the biology is complex. Stem cells must survive, integrate, connect appropriately, and function correctly in the receiving tissue. Challenges that require very detailed understanding of local signaling environments, and that have not yet been reliably met for most applications. Tissue engineering, the construction of replacement tissues outside the body, using combinations of cells, scaffolding materials, and bioreactive systems, has made significant progress in producing structures of limited complexity. Replacement skin for burn wound coverage, engineered bladder tissue, cartilage constructs, and blood vessel grafts have been developed and used clinically in research contexts. The engineering of more complex organs, liver, kidney, heart, with their intricate three-dimensional architectures, multiple cell types, and dense vascular networks, remains a much longer-term challenge, requiring advances in vascularization, scaffold design, and cell sourcing, gene therapy, the delivery of functional genetic material to cells to correct disease-causing mutations or introduce therapeutic functions, is advancing rapidly in certain specific applications. In the context of healing, gene therapy approaches are being explored to deliver growth factors directly and sustainably to wound sites, to correct the genetic defects that underlie conditions like epidermolysis bullosa, a severe skin fragility disorder, and to modulate the immune environment of healing tissues. Early clinical results in some of these applications have been encouraging. Bioelectricity represents an area of particular scientific fascination. Living tissues generate and maintain endogenous electrical fields, and there is growing evidence that these fields play active roles in directing cell migration and tissue patterning during both development and wound repair. The directional migration of keratinocytes during reepithelialization, for instance, appears to be guided in part by the electric field generated by ion transport across the wound epithelium. Research is exploring whether externally applied electric fields, applied through various devices to chronic or impaired wounds, can accelerate healing by augmenting or mimicking these endogenous electrical guidance cues. The field is early, but genuinely interesting. The gut microbiome has emerged as an unexpected but increasingly recognized participant in systemic health and potentially in healing responses. The trillions of microorganisms inhabiting the human gastrointestinal tract have profound effects on immune system development and tone, on inflammatory signaling, and on metabolic function, all of which intersect with healing. Research is beginning to explore whether the composition of the gut microbiome influences healing outcomes, and whether microbiome-targeted interventions might modulate healing responses. Artificial intelligence and computational biology are beginning to transform the research landscape across all areas of biology, including healing science, enabling the analysis of large, complex biological datasets at scales and speeds that were previously impossible, accelerating the identification of therapeutic targets, and supporting the design of clinical trials. None of these directions is a guaranteed solution to the current limits of healing science. None of them is ready, today, to do what popular imagination often wants science to do: to simply repair any injury, to regenerate any tissue, to make the body whole from any damage. The science is real, the progress is genuine, and the trajectory is toward greater capability. But it is a long road, and honest communication about where it stands matters. We have traveled far in this exploration, from the surface of skin in the first seconds after a cut, down through the stages of inflammation and repair, into the architecture of healing bone, and the rewiring of injured brain tissue, through the chemistry of sleep, and the physiology of stress, into the biology of emotional recovery, and the mechanics of scarring, through the changes that aging brings to repair capacity, and the honest limits of what healing can achieve, and finally through the horizon of what science is working toward. And throughout all of it, something has perhaps been building quietly in the background, a sense of the extraordinary coordination that underlies the whole enterprise. The way a damaged cell releases exactly the right alarm signals, the way neutrophils follow chemical gradients to the site, the way macrophages shift from clearing debris to directing construction, the way fibroblasts arrive at a wound they have never seen before, and begin producing exactly the collagen matrix the repair requires, the way keratinocytes, normally stationary, normally embedded in the architecture of skin, suddenly mobilize and migrate. None of this requires a plan in the cognitive sense. None of it requires a decision. The cells do not know what the outcome should be. They do not hold a blueprint of the healed wound. They simply respond to the molecular signals in their immediate environment, according to the instructions encoded in their DNA, instructions shaped, refined, and selected by billions of years of evolution, into a set of responses that, in the aggregate, produce healing. This is one of the most profound ideas in all of biology. That vast, coordinated, functional complexity can emerge from the local, individual behavior of components that have no awareness of the whole. A fibroblast migrates toward a higher concentration of a growth factor. It does not know it is healing a wound. It follows a chemical gradient. A keratinocyte moves across the wound surface in the direction that restores contact with its neighbors. It does not know it is closing the epidermis. It follows the signal of reduced contact inhibition. A macrophage transitions from inflammatory to repair-promoting signaling. When the molecular balance in its local environment shifts, it does not know it is managing a healing process. It responds to what its receptors tell it. And out of all these individual, local, molecular responses, none of which involves awareness or intention, emerges the global phenomenon of wound healing. A closed wound, restored barrier, resolved infection, rebuilt structure. This is the principle of emergence. In complex systems, behaviors and properties arise at the system level that are not present or apparent in the individual components. The behavior of a flock of starlings, the extraordinary fluid murmurations that change shape in the sky, cannot be predicted from studying a single starling. The individual bird follows simple rules. The collective follows no plan. And yet the collective is capable of producing shapes and movements, of breathtaking coordinated complexity. Healing is biology's murmuration. Millions of cells, each following their own molecular rules, in their own local environment, produce outcomes of systemic, functional coordination that no single cell could design or intend. There is something genuinely beautiful in this, not the pseudoscientific beauty of mystical narratives that claim the body is guided by consciousness or energy or intention, but the deeper, harder, more real beauty of emergence, the beauty of discovering that extraordinary complexity and coordination can arise from the faithful, distributed, local behavior of matter, following physical and chemical laws. And this, perhaps, is the most important gift that simple science explanations for beginners can offer. Not just the specific facts about inflammation or collagen or neuroplasticity, but the broader understanding that the body is not a black box of mystery. It is a comprehensible system, one whose complexity we are still working to fully understand, but whose principles, the principles of molecular signaling, of cellular response, of emergent coordination, are open to inquiry, illuminated by research, and available to anyone who is curious enough to look. The cells of your body are not intelligent in any way that resembles human intelligence. They have no awareness, they have no plan, but through billions of years of evolution, and the patient selection of molecular machinery that works, they have acquired something that functions. At the systems level, like intelligence, they respond to the right signals with the right behaviors. They produce, collectively, outcomes that serve the survival and function of the whole. Call it the quiet intelligence of cells. Not consciousness, not intention, just the accumulated wisdom of evolution, encoded in molecular form, and expressed every moment, in every living body. We return, at the end, to where we began. A small cut, a thumb pressed briefly against the sharp edge of something ordinary. The brief sting of it, the red appearing at the margin of the break. We have followed that moment through its entire biological arc now, from the first vasoconstriction in the seconds after injury, through the platelet aggregation and the clotting cascade, through the days of inflammation and immune response, through the proliferative phase of fibroblast activity and collagen deposition, through the slow weeks of remodeling, during which the granulation tissue is gradually, patiently converted into functional scar tissue. That entire journey, those weeks of quiet, meticulous, molecularly orchestrated work, will have unfolded largely without any awareness on your part. You will not have felt the fibroblasts arriving at the wound margins. You will not have perceived the growth factors diffusing through the clot toward the surrounding tissue. You will not have been aware of the macrophages transitioning from cleanup to coordination. You will not have sensed the keratinocytes beginning their long slide across the wound surface, or the new capillaries pushing their way into the granulation tissue. You will simply, one day, have glanced at your thumb and found it healed. This is, perhaps, healing's most characteristic quality. It is almost entirely invisible to the one it is happening to. And it is happening, right now, all over your body. The lining of your small intestine is replacing cells shed in the normal course of digestion. An entirely new epithelium every few days. The marrow of your long bones is producing hundreds of thousands of new blood cells every second. Red cells to carry oxygen. Platelets for clotting readiness. White cells for immune defense. The epithelium of your airways is clearing inhaled debris. On a slow upward escalator of mucus-covered, ciliated cells, your DNA repair enzymes are constantly scanning your genome for breaks and mismatches, correcting errors before they can propagate. Your liver is processing the metabolic byproducts of yesterday's meals. Your lymph nodes are sampling the contents of lymphatic fluid from every corner of your body, checking for signs of infection or abnormality. Your immune system is conducting its endless, quiet patrol. None of this requires your permission. None of it requires your instruction. None of it asks for your attention or your gratitude. The body's maintenance and repair systems operate continuously, at scales and speeds and in dimensions that lie entirely below the threshold of conscious awareness, proceeding with or without any acknowledgement from the mind that inhabits the body in which they work. We have, in the course of this long exploration, learned that healing is not one thing. It is a constellation of overlapping, interdependent processes. Inflammatory, immunological, cellular, hormonal, neural, structural, that unfold in waves across time, each triggered by and dependent on the ones that preceded it, each creating the conditions for the ones that will follow. We have learned that healing operates through molecular conversation at scales far below visibility, through the coordinated behavior of billions of cells following local signals, through the architecture of tissues shaped by both development and evolutionary history. we have learned that healing is not always perfect, that it leaves marks, that it compensates and adapts where it cannot restore, that some tissues heal with more fidelity than others, that age changes the terms on which healing proceeds, that the systemic biological environment, shaped by sleep, by stress, by social connection, by the hormonal climate, affects the conditions under which healing takes place. That medicine, at its best, understands healing deeply enough to support and enhance it rather than replace it. We have learned that there are genuine limits, tissues and structures whose regenerative capacity is insufficient for full recovery after serious damage, and that these limits, while sobering, are not the end of the story. They are the honest frontier that drives regenerative science forward. And we have learned something perhaps more fundamental than any specific mechanism or any individual cell type. That healing is what life does with damage. That every living system, every cell, every tissue, every organism carries within it some capacity to respond to disruption and move toward restoration. That this capacity, assembled and refined by evolution over immense spans of time, is among the most ancient and most defining characteristics of what it means to be alive. It is quiet. It is constant. It does not ask to be noticed. In the middle of the night, while you sleep, and growth hormone moves through your bloodstream in its slow surge, and glymphatic fluid washes through the channels of your brain, and muscle fibers reassemble their damaged proteins, and bone tissue is broken down and rebuilt, and immune cells complete their patrol of every tissue they can reach. Healing is happening. When you wake, you will not be aware of it. You will move through your morning, and the biological work of the night will have proceeded without any acknowledgement from you, without any gratitude or recognition or even curiosity, simply because that is what the body does. It tends to itself, in every tissue, at every hour, through every season of a human life. It moves, always, toward balance, not toward perfection, not toward permanence, not toward some idealized state that exists only in imagination, but toward the continued functioning of the whole, toward another hour of breathing, and moving, and sensing, and thinking, toward the quiet, unremarkable, extraordinary fact of continued life. Healing is not magic. It is biology, ancient, patient, molecular, and quietly miraculous in its ordinary persistence. And whether we ever pause to notice it or not, whether we ever understand it fully or not, it continues, quietly, without interruption, in the dark.